Okay, I'll give an example of non-uniform circular motion, and this is a loop-the-loop. So the idea is I have something like a roller coaster car that's going to go around in a loop and then carry on its merry way. Could be an airplane doing a loop, or a roller coaster, or a Hot Wheels car, or lots of different examples. And it always looks surprising that something could go around in a circle that is oriented vertically. So for this particular problem, it's a roller coaster scale. That's the radius, and that is a radius of 10 meters, so not from your Hot Wheels set. And what we want to figure out is what is the minimum speed that the roller coaster is going to have at the top to make it around the loop-to-loop, to just make it around. If it goes faster than that, definitely fine. It will go around, and then there will be a normal force that the track pushes down on the car with. And if it's going too slow, then it won't make it to that highest point. It's going to fall off the track before it reaches there. And that would be the bad juju. So what we want to find is what is the minimum speed at the top, so it just makes it around the loop-to-loop. So let's talk about the free body diagram. The roller coaster car is just right there. So here's my really advanced drawing of a roller coaster. Forces acting on that. It's going to have a weight, mg. It may also have a normal force from the track pushing down. So I'm going to put that in as well. And then if we add those two vectors together, that's going to give us our net force, which is going to be the force in the radial direction. So I'll call that F net, its radial component. So now we know a little bit about this radial component of the net force. To undergo circular motion at the top, whether uniform or not, but to have circular motion at the top, we know the following has to be true. The radial component of the net force, which is equal to mass times the radial acceleration, is mv squared over r. We have two things to make that out of. We have the normal force pointing in towards the center of the circle and the weight. Okay. Let me isolate just the last two in that set of equalities. So let's look at just the mv squared over r is equal to n plus the weight. Now when v, the speed, goes to the minimum speed it can make to go around, then the left-hand side is going to be as small as it can be. Track is fixed, mass is fixed. I need the right-hand side to be as small as it can be. And that's going to be the case when the normal force goes to 0. And then I'm only left with the weight. So it's the weight of the car, the roller coaster, that's providing the radial force to undergo circular motion. So at the slowest speed that just makes it, there is no normal force at the top at all. Okay. And then if it goes faster than the minimum speed to complete the loop-de-loop, all you're going to require is a bigger and bigger normal force of the track pushing down on the roller coaster. So at that minimum point for the speed, so at v min, our equation is going to simplify. It's mv squared over r is equal to mg. And now the mass of the roller coaster car cancels out because it's on both sides. And I can solve for v. The speed is going to be radius of curvature of the track times the acceleration due to gravity, all square root. So we put in values. Our roller coaster is on Earth, and the radius was given as 10 meters. Have 10 meters times 9.8 meter per second squared, and take the square root. And that's going to give us a speed, it's basically, it's 10 times 10, and then the square root, so it shouldn't be too surprising. The answer is just right at 10 meters per second. And that is the minimum speed to make a loop-de-loop on planet Earth for that given track size. If the track is bigger, you're going to have to go faster at the top. And if you're thinking of building this on some other planet, you need to take G into account there before you built your amusement park for Elon Musk on Mars.